At 5 a.m. this morning, fire erupted from the earth beneath a temple in southern Taiwan. Not from magma, not from lava, from mud. Flames shot 2 meters into the air as brown sludge boiled up through 5 separate vents, transforming farmland into a field of burning slurry. The ground shook, the air filled with the sharp smell of methane and sulfur, and villagers who had seen this before knew exactly what it meant. The Wandan mud volcano had awakened again, but this time something was different. One of the vents tore open directly beneath a house. What drives mud to explode with such violence? Why is this happening more often? And what does it mean when the ground itself begins to burn? The eruption began without warning in Wandan village, Wandan Township, Pingtung County. Residents near Huangyuan Temple heard a deep rumble at dawn, followed by the unmistakable hiss of escaping gas. Within minutes, 5 vents had opened across the landscape, each one discharging a violent mixture of mud, water, and methane. The tallest plumes reached 2 meters high. Thick brown mud fountained upward in rhythmic pulses, splattering across roads and fields. The smell was overwhelming, a mixture of rotten eggs and wet earth that clung to clothing and skin. Local farmer Lin Mei Hua, whose house sits close to the eruption zone, described the moment the ground tore open. "It was like a dragon waking up," she said, her voice still tight with the memory of that pre-dawn shock. The ground trembled, then the first jet of brown water shot skyward, hissing and bubbling. Temple abbot Chow Pao Hui rushed outside as the first vent erupted just 50 meters from the temple's main gate. He had witnessed the previous 10 eruptions at this site, but never one this close. The mud was hot to the touch, around 38 degrees Celsius, warm as human blood. Its consistency was strange, more liquid than clay, about 70% water mixed with fine sediment and invisible pockets of gas. But the real danger was not the heat or the mud. The methane content in the erupting gas reached over 90% by volume. This invisible fuel transformed each vent into a potential torch. Local residents, following a practice developed over previous eruptions, threw burning rags into the vents. Flames erupted instantly, creating crowns of fire that burned above the bubbling mud for hours. Village Chief Chen Yui arrived within minutes of receiving reports. His first concern was not the spectacle, but the farmland. The mud was spreading fast, flowing downhill toward rice paddies and vegetable plots. He immediately coordinated teams to dig diversion channels, crude trenches carved into the soil to redirect the flow away from crops. The work was urgent and physical. Every hour of delay meant more land buried beneath hardening sludge that would take weeks to remove. The eruption continued for more than 10 hours, finally subsiding around 3:40 in the afternoon. Throughout the day, the vents pulsed and hissed. When the activity finally ceased, what remained was a gray-brown field of cooling sludge that would harden into a smooth clay-like surface difficult to break apart or plow under. Taiwan sits at one of the most geologically violent intersections on Earth. The Philippine Sea Plate collides with the Eurasian Plate at approximately 80 millimeters per year. This convergence has built mountains, fractured bedrock, and created deep faults cutting through sedimentary layers thousands of meters below the surface. Along Taiwan's western foothills, these faults penetrate Pliocene-age mudstone formations, deposited millions of years ago when the region lay beneath a shallow sea. Bacteria broke down organic matter in the oxygen-starved depths, producing methane gas that dissolved into groundwater trapped under immense pressure. Pressure comes from multiple sources: rapid sediment deposition, tectonic compression from colliding plates, and accumulating methane itself. When pressure exceeds the strength of overlying rock, the system fails. Mud volcanoes form along these failure points, typically at fault intersections where weaknesses in the rock provide pathways to the surface. In Wandan, the Chisan Fault meets a layer of water-saturated mudstone. When stress builds beyond a critical threshold, the pressurized mixture of water, fine sediment, and gas bursts upward through fractures, creating what scientists call a mud geyser rather than a traditional mud volcano. The difference is significant. Most mud volcanoes worldwide produce cold, thick mud that oozes slowly from cone-shaped mounds. Wandan behaves differently. Its eruptions are violent, water-rich, and explosive. The fluid shoots upward in powerful jets, more like a geyser than a typical mud flow. This hybrid behavior reflects the high water content of the aquifer and the rapid pressure release when the seal breaks. The energy behind each eruption is comparable to opening a champagne bottle. Once the seal fails, dissolved gas comes out of solution instantly, propelling the mixture skyward. Scientists describe this as a salse, a term borrowed from Italian geology to describe mud features driven by pressurized gas rather than heat.
Wandan's mud volcano first appeared in 1977 after Typhoon Felma triggered landslides that broke into the underlying aquifer. Since that initial breach, the system has erupted at least 11 times. The frequency is accelerating. In the past 3 years alone, 10 eruptions have occurred, with intervals shrinking from years to months. The November 12th eruption marked the 11th documented event in just over 3 years. The previous eruption occurred only 6 months earlier, in June 2025. Before that, eruptions were recorded in July 2024, February 2023, and multiple times in preceding years. Each event follows a similar pattern. Early morning onset, multiple vents opening near the temple, flames ignited by locals, and mud flows diverted by emergency channels. But the pattern is not just repeating, it is intensifying. Dr. Lin Yi-chun, a volcanologist from Academia Sinica who arrived at the site with thermal cameras and gas sensors, described this as the strongest eruption here since 2005. Real-time measurements recorded gas flow rates and particle sizes that exceeded previous events. The water temperature remained consistent at 38 degrees Celsius with a pH of 7.8, slightly alkaline. The mud itself, when dried, becomes a smooth clay valued by local potters, but during eruptions, collection is impossible and dangerous. What makes Wandan unusual, even among mud volcanoes, is its location and behavior. Fewer than 1,100 mud volcanoes have been identified worldwide. Most are found in Azerbaijan, Indonesia, Pakistan, and parts of Italy and Romania. Taiwan hosts more than 100 gas seeps and mud volcanoes, concentrated along tectonic sutures where fault zones provide natural pathways for gas migration. Chang Pao-hu, the temple abbot, has become an unlikely chronicler of the volcano's moods. He lives at Huangyuan Temple, a small structure that sits within meters of the most active vents. Over the years, he has developed an informal system for reading the volcano's behavior. Ground tremors, sometimes detectable days before an eruption, provide the earliest warning. Bubbling sounds emerge from cracks in the soil. The smell of gas becomes stronger, drifting through the temple grounds like an invisible tide. On November 12th, Chang woke up at 4:30 a.m. to the rumble. He stepped outside into darkness and watched the first vent open just beyond the temple gate. The mud shot upward with a hiss, and within minutes locals arrived with burning rags to ignite the methane, creating flames that crowned the vent. He has witnessed this spectacle many times, but familiarity has not erased the unease. Each eruption brings uncertainty. Will events open in the same locations? Will the mud flow toward the temple? Will the flames spread? This time, one family had evacuated days earlier, sensing the ground's restlessness. Their caution proved justified when a vent opened directly beneath their home, leaving the structure sitting at the center of a mud field, its foundation compromised. Chang maintains detailed video records of each eruption, sharing footage with geologists who study the volcano's behavior. His documentation has become essential data for researchers trying to predict when and where the next eruption will occur. The financial toll on local residents is mounting, though exact figures remain difficult to quantify. Families near the vents face recurring costs for repairs as hardened mud infiltrates drainage systems, cracks foundations, and ruins crop soil. Insurance companies refuse to cover volcanic damage, citing exclusion clauses. Property values have plummeted, with few buyers willing to invest in homes next to an unpredictable natural hazard. Yet, many residents stay, bound by generations of family history and the simple economics of having nowhere else to go. The methane erupting from Wandan is not just a local curiosity, it is a global climate concern. Methane is a greenhouse gas 28 times more powerful than carbon dioxide over a century. Natural geological sources, including mud volcanoes, contribute an estimated 45 teragrams per year to the global atmospheric methane budget, roughly 8% of total emissions. Studies across Taiwan revealed these features emit methane through both macro seepage from visible vents and micro seepage from invisible diffuse emissions across mud platforms. The microseepage can exceed visible emissions by orders of magnitude as gas percolates through sediment pore spaces.
Research teams have measured methane emissions from Wandan and similar sites using closed-chamber methods and satellite observations. Estimates suggest that a single active mud volcano can release tens to hundreds of tons of methane per year. When multiplied across Taiwan's dozens of active sites, the cumulative atmospheric impact becomes significant. What makes terrestrial mud volcanoes particularly important is their direct connection to the atmosphere. Unlike submarine mud volcanoes, where seawater can absorb and oxidize much of the methane before it reaches the air, terrestrial systems like Wandan release their gas directly into the sky. The methane composition at Wandan is thermogenic, formed through thermal breakdown of organic matter at depth. Isotopic analysis from research studies shows delta 13C values of -32.9 to -36.2 per mil, consistent with gas from coal-bearing sediments. Based on these signatures and local geothermal gradients of 25 to 30 degrees per kilometer, researchers estimate the methane originates from 2 to 9 kilometers depth. When locals ignite the vents with burning rags, they are converting methane to carbon dioxide and water vapor through combustion. While CO2 is also a greenhouse gas, its warming potential over a century is roughly 28 times lower than methane's. Flaring represents a form of harm reduction, though the practice developed from practical observation rather than climate science. But not all the methane burns. Between eruptions, invisible seepage continues. The escalating frequency of Wandan's eruptions points to a system under increasing stress. 11 eruptions in 3 years represent dramatic acceleration compared to earlier decades when eruptions were separated by years. The intervals between events are shrinking from months to weeks. What drives this change? Tectonic stress from ongoing plate collision may be increasing, squeezing the subsurface aquifer and raising pressures. Groundwater fluctuations influenced by seasonal rainfall and extraction can alter underground force balances. And once breached, subsequent eruptions become more likely as weaknesses remain. Each eruption modifies the subsurface plumbing as new fractures open and old pathways widen. Dr. Xu Shiwei, a geologist with Taiwan's Central Geological Survey, describes the system as a pressure cooker with a cracked lid. But predicting exactly when pressure will exceed the breaking point remains beyond current capabilities. Seismic monitoring detects micro-earthquakes that often precede eruptions. Ground deformation measurements track surface bulging or sinking. Gas sensors identify changing methane concentrations days before events. But none provide definitive forecasts with meaningful lead time. Residents rely on traditional indicators: gas smell, ground vibrations, bubbling sounds. These offer only hours of warning at best, and sometimes no warning at all. The November 12th eruption highlighted a growing vulnerability. According to reports from multiple observers, one vent opened directly beneath a residential structure, an event that had not occurred in previous eruptions. This development suggests that the subsurface fracture network may be expanding, reaching into areas previously considered safe. If the pattern continues, more homes and infrastructure could be at risk. The impact on agriculture is immediate and measurable. Mud flows bury topsoil, rendering fields unusable for months or even years. The sludge hardens into a dense, impermeable layer that prevents water infiltration and root penetration. Farmers must either excavate the mud, an expensive and labor-intensive process, or abandon the land. In the November eruption, village authorities acted quickly to dig diversion channels, redirecting the mud away from active farmland. But this is a temporary measure, effective only during the eruption itself. Once the mud spreads beyond the channels, removal becomes far more difficult. The economic burden accumulates with each event. Small farmers operating on thin margins struggle to absorb repeated crop losses and land restoration costs. Some have already ceased planting near the vents, effectively ceding the ground to the volcano. Infrastructure damage extends beyond agriculture. Roads crack as subsurface gas escapes through fissures, drainage systems clog with mud. Emergency responders face new challenges with each unpredictable eruption. The cumulative concern is mounting. Each event weakens the ground, opening new fractures and destabilizing foundations. Buildings near vents show stress, cracked walls, uneven floors, warped frames. And the events show no sign of stopping.
Scientific monitoring of Wandan has intensified. Research teams from Academia Sinica, the Central Geological Survey, and universities have deployed instruments tracking gas emissions, seismic activity, and ground deformation. Drones map temperature distributions, gas sensors measure methane in real time, seismometers detect microtremors, GPS stations track millimeter-scale elevation changes. This data is critical for understanding the system, but it also reveals knowledge limits. Scientists can describe what happens beneath Wandan in precise detail. They can map fault networks, measure gas flux, and calculate pressure thresholds, but they cannot predict when the next eruption will occur with certainty. The reason is simple. Mud volcano eruptions are triggered by a complex interplay of factors that remain difficult to model. Tectonic stress builds gradually over time, but the exact moment when pressure exceeds rock strength is influenced by countless variables: groundwater levels, temperature fluctuations, microseismic events, and even atmospheric pressure changes. Weather patterns complicate the picture. Heavy rainfall infiltrates the subsurface, altering fluid pressures. Droughts reduce aquifer recharge. Typhoons have historically triggered eruptions by destabilizing slopes and opening fractures. The potential role of climate change in eruption frequency remains an open question. If warmer temperatures increase evaporation rates, this could alter groundwater dynamics, affecting subsurface pressure. Yet establishing direct causation requires decades more data than currently exists. What scientists do know is that Wandan is not unique. Similar systems exist across southern Taiwan and in dozens of other countries. The global pattern is one of increasing awareness rather than increasing activity. Many mud volcanoes go unmonitored, their eruptions undocumented. Wandan's visibility is partly a function of its location near populated areas and the dedication of local observers like Changpao Hui who document each event. The scientific community agrees on several key points. The gas is thermogenic, sourced from deep sedimentary layers. The eruptions are driven by overpressure in a fractured aquifer. The frequency is increasing, and the system will continue to erupt. What remains unknown is the timeline, the intensity, and the ultimate extent of the hazard. Scientists know that Wandan's mud volcano is driven by methane from sedimentary layers 2 to 9 kilometers below the surface. They know the gas is thermogenic, formed by thermal maturation of organic matter over millions of years. They know the eruptions occur along the Chishan Fault, where tectonic stress from the Philippine Sea Plate collision creates pathways for fluid migration. They know the system has erupted at least 11 times in 3 years, with intervals shrinking. They know each eruption releases tens to hundreds of tons of methane, a potent greenhouse gas. And they know the vents are opening in new locations, including beneath residential structures. But what scientists do not know is far more extensive. They cannot predict when the next eruption will occur. They cannot determine where new vents will open. They cannot calculate how long the current acceleration will continue or when, if ever, the system will return to a less active state. They do not know if the fracture network is still expanding, potentially threatening more homes and infrastructure. They do not know if climate change is influencing eruption frequency through altered rainfall patterns or groundwater dynamics. And they cannot say with certainty whether the total methane emissions from Wandan and similar systems are increasing globally or simply becoming more visible through improved monitoring. The fundamental problem is that mud volcanoes operate on geological timescales that humans struggle to comprehend.
What appears to be an acceleration over 3 years may represent normal variability on a scale of decades or centuries. Or it may signal a genuine shift in the system's behavior, a precursor to even larger events. Without longer historical records, distinguishing between these possibilities remains beyond current analytical capabilities. Erosion models suggest that mud volcanoes can remain active for thousands of years. They build cones, erode, rebuild, and shift locations as subsurface pathways change. The Wandan system, born in 1977, is geologically young. Its long-term evolution is impossible to forecast. The area's classification as high risk has led insurance providers to exclude volcanic coverage, while the market for properties near active vents has contracted sharply. Residents face the reality that at any moment, the ground beneath them could open and erupt. No one can tell them if the worst has already happened or if it is yet to come. Taiwan's mud volcano systems span multiple regions across the island, with populations in the hundreds of thousands living in areas where these features occur. Most will never experience an eruption, but for those in Wandan village, the question is not if another eruption will occur, but when, where, and how much damage it will cause. The temple still stands, the fields are being cleared, and the vents, for now, are silent. But beneath the surface, pressure is building again.